Hello students, I am Equationof. Welcome to my YouTube channel Best Physics Guide by Equationof. Today I am going to discuss about the equations of motion, Newton's formula, friction, rocket motion, the apparent weight of a person inside a lift, and some problems related to pulley. Let's watch the video and please subscribe my channel. From Newton's law of motion, we know that F is equal to ma, where F is the resultant force acts on the particle or on the body, and A is the acceleration of that particle or acceleration of that body, and M is the mass of that particle or mass of that body. The friction, we know that friction always acts against the relative motion between the body and the surface. The friction acts on the body is equal to mu into n, where mu is the coefficient of friction between the body and the surface on which the body is placed, and n is the normal reaction. Capital N is the normal reaction acts on the body. Let a body is placed on a horizontal surface. Capital T is the applied force, and therefore the body moves along the direction of the force with an acceleration small a. Mg is the weight of the body, where g is the acceleration, small g is the acceleration due to gravity. Capital N is the normal reaction acts on the body. Here capital N is equal to mg, and friction acts on the body is mu into n, which is always acts opposite to the motion of the body. Therefore the resultant force acts on the body is ma is equal to T applied force minus friction mu into n. This gives ma is equal to T minus mu into mg, since n is equal to mg. This is the equation of the motion of a body for a body which moves along a horizontal surface. For a smooth surface, mu is equal to 0. That's why the equation of the motion of the body on a smooth surface, smooth horizontal surface, is T is equal to ma. When a body is placed on an inclined surface, the angle between the horizontal surface and the inclined surface is theta. The body falls through the inclined surface with an angle A. Here the coefficient of friction between the body and the inclined surface is mu. Normal reaction is n, and here n is equal to mg cos theta, and the component of the weight mg sin theta, which is responsible to move the body downward direction. That's why the equation of the motion of the body is ma, that is resultant force, is equal to mg sin theta minus mu into n. This gives ma is equal to mg sin theta minus mu mg cos theta. Therefore a is equal to g into sin theta minus mu cos theta. This is the equation of the motion of that body. Now the body is moved upward direction with an acceleration a by some external force capital T. Here T is the applied force which moves the body through the inclined plane in upward direction. Here the friction mu into n acts downward direction through the inclined plane. Therefore the equation of motion will be ma, that is resultant force, is equal to T, that is applied force, minus the force which acts against the applied force, that is mg sin theta plus mu into n. This gives ma is equal to capital T minus mg whole into sin theta plus mu cos theta. Since here normal reaction n is equal to mg cos theta. This is the equation of the motion of this body. Now a body is placed on a horizontal table having coefficient of friction mu with the table and the body. Here m2 is the mass of the body and it is connected by a string through a frictionless pulley, and this string is attached with another body having mass m1. Now the whole system moves, that is the body m1 and the body m2 moves with an acceleration a. Capital T is the tension of the string. The equation of the motion for the first body is m1 into a, that is resultant force, is equal to m1g minus t. Since the body for the m1, this body moves in the downward direction, that's why m1g is greater than t, tension of the string. That's why m1a, that is resultant force, is equal to m1g minus t. And the equation of the motion of this body is m2a is equal to t, that is tension minus friction mu m2g. Adding equation 1 and 2, we get a is equal to m1 minus mu into m2 whole divided by m1 plus m2 whole into g. And putting the value of a in the second equation, we can get capital T is equal to m1 m2 whole into 1 plus mu whole into g divided by m1 plus m2. For a smooth surface, that is when the friction between the body and the table is negligible, then the value of mu becomes 0. Now two bodies are suspended by a string through a frictionless pulley in a horizontal in a vertical plane. Okay, here the mass of the first body m1 is greater than the mass of the second body, that is m1 greater than m2. Therefore the first body, that is m1, moves downward with an acceleration a, and the second body moves upward with an acceleration a. T is the tension of the string. The equation of motion for the first body is m1a is equal to m1g minus t. Since here m1g is greater than t, the equation of motion of the second body is m2a is equal to t minus m2g. Adding equation 1 and 2, we have a is equal to m1 plus m2 is equal to m1 minus m2 whole into g. This gives a is equal to m1 minus m2 whole divided by m1 plus m2 whole into g. This is the acceleration of the two bodies. Now putting the value of a in equation, either equation 1 or either equation 2, we get the value of t, that is tension of the string. T is equal to 2 m1 m2 whole divided by m1 plus m2 whole into g. The tension of the string which suspend the pulley is 2t. Okay. Here two bodies m1 and m2 are suspended by strings through a vertical plane. Here m1 greater than m2. Here m1 is greater than m2 and m1 is attached with a fixed frictionless pulley and M2 is attached with a movable pulley. T is the tension of the string. The first body, that is M1, moves vertically downward with an acceleration A, and the second body M2 moves vertically upward with an acceleration A by 2. The acceleration of the second body becomes A by 2 since it is connected with a movable pulley. Therefore, the equation of the motion of the first body is M1A is equal to M1G minus G. The equation of the motion of the second pulley is M2A by 2 whole divided by 2 is equal to 2T minus M2G. Now multiplying the first equation by 2, multiplying equation 1 by 2, we have 2m1a is equal to 2m1g minus 2t. Now adding equation 2 and 3, we have a is equal to 2 into whole into 2m1 minus m2 whole into g divided by 4m1 plus m2. This is the acceleration of the first body m1, and the acceleration of the second body is 2m1 minus m2 whole into g divided by 4m1 plus m2. Now I am going to discuss about reaction in a lift. Let us consider a body is placed inside a moving lift. The lift moves with an acceleration A in upward direction. Capital R is the reaction force acts on the body. mg is the weight of the body. Here capital R is also the applied force by which the lift is moved in upward direction. Therefore, the equation of the motion of the body will be Ma, that is resultant force on the body, Ma is equal to capital R minus mg, or equation of motion of the lift will be Ma is equal to capital R minus mg, or R is equal to m whole into g minus a. Since capital R is greater than mg, therefore the apparent weight of the body is increased. That's why when a person is standing inside a moving lift which moves upward direction, then the person feels that his weight increased. When a lift is moving vertically downward direction with an acceleration A, then its equation of motion will be Ma is equal to mg minus R. Here R is the reaction on the body. Therefore capital R is equal to m whole into g minus a. Now since R is negative, that's here R is less than mg. Since here R is less than mg, therefore the apparent weight of the body is decreased. Therefore when a person is inside a moving lift which moves vertically downward with some acceleration, then the person feels that his own weight is decreased. When the lift falling freely, then small a is equal to g, that is acceleration of the lift becomes small g. That's why the reaction force on the body R is equal to m into g minus g. This is equal to 0. That is the reaction, since the reaction force on the body becomes 0, therefore the apparent weight of the body becomes 0. This is known as weightlessness condition. This is known as weightlessness condition. When the lift is falling with an acceleration A which is greater than small g, that is acceleration due to gravity, then the equation of the motion becomes ma is equal to mg minus capital R. This is equal to capital R. This gives capital R is equal to m into g minus a. Since here magnitude of small a is greater than the magnitude of small g, that's why the magnitude of capital R, that is reaction force, becomes negative. This is known as super weightlessness condition. This is known as super weightlessness condition. In this case, initially the body moves upward with respect to the lift, and after some time the body touches the ceiling of the lift. This is known as super weightlessness condition. In this case, the body touches the floor of the ceiling of the lift. When the lift moves with uniform velocity, that is small a is equal to 0. In this case, we have R is equal to mg, since a is equal to 0. Therefore, when the lift moves with uniform velocity, then the apparent weight of the body is equal to the actual weight of the body on the surface of the earth. Now I am going to discuss about the theory of rocket motion. Let a rocket moves vertically upward with some velocity v after time t, small t, after the projection of the rocket. After some time dt, that is at the time t plus dt, the velocity of the rockets becomes v plus dv. Here dv is the increase of the velocity of the rocket. Some fuel from the rocket is ejected with some velocity u. Here dm is the mass of the ejected fuel. Here dm is the mass of the ejected fuel. U is the velocity of the fuel which is ejected from the rocket. The value of u remains constant with respect to the rocket. Here the velocity, the linear momentum of the rocket at time t is p1, and the linear momentum of the rocket and the ejected fuel with after time t plus dt is p2 with respect to the ground. Therefore, p1 is equal to linear momentum of the rocket at time t is p1 is equal to m into v, and the linear momentum of the rocket plus ejected fuel is p2 is equal to m minus dm. This is the mass of the rocket without the ejected fuel into v plus dv. Here dv is the increased velocity, v plus dv is the increased velocity after ejecting fuel, plus v minus u into dm. Here v minus u is the relative velocity of the fuel with respect to ground, and dm is the mass of the ejected fuel. Therefore, p2 is the linear momentum. P2 is the linear momentum of the rocket plus ejected fuel with respect to the ground. Now, the change in linear momentum during time dt is dp is equal to p2 minus p1. This gives dp is equal to m minus dm whole into v plus dv plus v minus u into dm minus m into v. This gives dp is equal to m dv minus u dm. This is the change of the linear momentum of the rocket. Now, the resultant force acts on the rocket is F is equal to dp dt is equal to, that is rate of change of linear momentum, is equal to m dv minus u dm whole divided by dt. Here the weight of the rocket acts against the resultant force. Therefore, F vector is equal to minus mg. And since the direction of v, that is velocity of the rocket, and velocity of the fuel are opposite to each other, therefore we can consider that v as a positive sign and the u as negative sign. Therefore, the equation of motion of the rocket becomes m dv plus u dm whole divided by dt is equal to minus mg, or dv is equal plus u dm by m is equal to minus gt. Now integrating both sides, we have dv, the lower limit of integration, this is 0 to v. Since the rocket initially is at rest, therefore the lower limit is 0, and after time t its velocity becomes v. Therefore integration 0 to t, integration 0 to v dv plus u, integration m0 to m dm by m. Here the initial mass of the rocket is m0, and after time t its mass becomes m, and minus g integration 0 to 2 t dt. This gives v plus u ln m by m0 is equal to minus gt. This is the equation of the velocity of the rocket after time t. At high altitude, we can neglect the acceleration due to gravity. Therefore, the expression of v becomes v is equal to minus u ln m by m0. This gives v is equal to u into ln m0 by m. This is the instantaneous velocity of the rocket at the high altitude. Here m0 is the initial mass of the rocket and capital M is the mass of the rocket after time small t, when the velocity of the rocket becomes v. Let mf be the total fuel of the rocket. Therefore, the maximum velocity of the rocket becomes Vmax is equal to u ln m0 whole divided by m0 minus mf. This is the maximum velocity of the rocket, where u is the velocity of the fuel. For today, I am going to complete my video, and thank you for watching my video, and have a nice day, and please subscribe my channel. Thanks once again.